can start the recording. Okay, so I think it's recording now. Yeah, okay. Now I have started the recording. So anyway, it's clear before the recording. So one of the example of the power series is e power x is equal to this, and the other one is sine of x. Sine of x is also a series. So this can be also represented by a power series. So it is 1 minus x square over 2 factorial plus x power 4 over 4 factorial minus x power 6 over 6 factorial, and then the pattern goes on. So this is for no, this is for the cosine of x, not sine. This is for cosine of x. Cosine of x. And for sine of x, it is x minus x cube over 3 factorial plus x power 5 over 5 factorial minus x power 7 over 7 factorial, and this goes on. So you can see that the cosine and sine series, the signs are changing from plus to minus to plus to minus, and then similarly this. But in cosine, you have first term as 1, and then you have the even powers of x divided by the same factorial, okay? And similarly in the sine, it starts from x, there is no one term over here, and the powers are in the odd, the powers are odd for x, and then the same factorial is over there. So in this way, we can memorize these series. So these are the three very commonly used series. So they are also called as the Maclaurin series. Okay, Maclaurin series. Okay, so there are certain properties of these series which we can use for the solution of the ordinary differential equations. So for example, if I take this series, and then there is actually a notation which we can use, which we can use for the summation for this series. This is called as the sigma notation. This notation, I have found it very useful. So this sigma notation says that it is the sum of these terms where the position of these terms, which is also the index of these terms, can be represented by m. So starting from 0, that means 0 is the first term, up to the last term, infinity, can be represented by some coefficients multiplied by the power of x. So this type of notation we can use for the solution of the ordinary differential equation, and that makes it makes the task rather quite convenient. Okay, so since in the solution of the ordinary differential equations, we also need to find the we also need to represent the derivatives. Okay, the derivatives as well. So for example, if I take this form of the power series, and I take its derivative, so f of x, so its derivative I can represent by like this. So because all of these are the polynomial terms, so its derivatives can be represented by like this. So a naught will vanish from here. Okay, a naught will vanish from here. So we will have one less term for the derivatives. So it means that the index value for this can start from 1. So anyway, so its derivative will be a1. It will start from a1 plus 2a2x, okay, 2a2x, and plus 3a3 x square, and so on. So by doing this, we can represent it in the sigma notation like this. So m will come over here, m will come over here, and then it will be am term, and then the power of x will be 1 less than m. Okay, 1 less than m. So we can represent these terms like this, and it will vary from m is equal to 1 to infinity. So because the first index term was vanished in this case. Okay, so in similarly, the second derivative for this series can be represented like this. So second derivative can be also represented like this. M is equal to, in this case, m will equal to 2 to infinity, and then this m minus 1 will also come over here. So m minus 1 into am and x power m minus 2. Okay, so am will remain the same. The only thing will be the these m and m minus 1 terms, and the power of x power minus 2, that will change. So we can use these kind of relationships in the solution of the ordinary differential equations using the power series. Okay, so this is one thing, and the other thing is that why do we need to use the power series for the solution of the ordinary differential equations? The answer is that not the solution of not every ordinary differential equation is possible by using the analytic methods. Okay, so for example, in the case of the first order equation, the method of separation of variables, using the integrating factors, or in the case of second order equations, using the method of the undetermined coefficients, these kind of things. So especially for those equations in which we have the variable coefficients of the equation. So for example, this is the second order equation, y double prime a1 y double prime plus a2 y prime plus a3 y is equal to some function of x. So in most of the cases, depending on this function of x, we can find the solution, because a1, a2, and a3 are the constant values. So if for example, if this is essentially equal to 0, so the solution of this will be given by the roots of the characteristic equation. However, for certain equations, for example, where the coefficients are not constant, coefficients are variables in x, so it is not possible to find an analytic solution. So for example, let me see, example is, for example, this equation, y double prime minus y prime plus x square y. So this is a linear equation. This is a linear equation because it is y, all terms of y are linear, and then it is a second order differential equation, homogeneous equation, but its coefficients, one of the coefficient is x square over here. However, we don't have any method over up to now which can give us some analytic solution of this. By analytic solution, I mean the solution in terms of some other function. So for example, the solution of this y double prime minus 3y plus 4, 3y prime minus 4. So we know that it's, sorry, it is, if it is minus 4. Minus 4y. So we know that its characteristic equation is, so we can solve its characteristic equation is m square minus 3m minus 4 is equal to 0. So we can find its characteristic, the roots of this characteristic equations are like this, okay? Minus 4 plus 1, yeah, that's what it will be this. So its solution will be y is equal to y of x is equal to c1 e power 4t plus c2 e power minus x into x. Okay, c1 e power 4x plus c2 e power minus x. So from this its characteristic equation, we can find the solution immediately. However, for this, we don't have any such characteristic equation. So therefore, we cannot find its solution in terms of these elementary functions. So e power x, e power 4x, sine x, cosine x, these are the elementary functions. So we cannot find the solution in terms of some elementary functions for this type of equation. So therefore, for the solution of these type of equations, we use the power series for the solution of the ordinary differential equations. Okay, so without spending much more time on this introduction, in fact, I have provided some more introduction into my uploaded videos, so you can look at this. So let's solve some examples. Okay, so for example, in the yeah, so for example, in the uploaded lecture, I have used these kind of equations. So for example, y prime minus y is equal to 0. So it's what is its solution, or maybe y double prime minus y is equal to 0. Okay, so we know that we can analytically find this solution, and then we can also verify it. Okay, so for this live lecture, I can take another example. Okay, so let's take the example of is an equation which is y double prime plus y is equal to 0. Okay? Y double prime plus y is equal to 0. That means d2y over dx square plus dy is equal to 0. So we know that its characteristic equation is m square plus 1 is equal to 0. M is equal to plus minus I, and its solution is a cosine x plus b sine x. So we already know the solution. Okay, so let's try to solve it with the help of the power series, and we should get the same solution. So this will illustrate you the method, and also it will also a kind of like a soft proof that this method works. So for the solution of this equation, so we have to represent these y double prime and y with their sigma notations. So in the previous slide, if you see that the sigma notation for the second derivative was this. Okay, so we can use this. So we assume that the solution is represented by this equation, this power series a naught plus a1 plus a1 x plus a naught a2 x square, and then its second derivative is represented by this series. Okay, this sigma notation. So y double prime I will represent by this. So sigma m is equal to 2 to infinity m minus m into m minus 1, okay, into am x power m minus 2. So this will be the representation of y double prime. And then we have plus y. So plus y is the sigma notation of from m is equal to 0 to infinity am x power m, and that is equal to 0. So in this way, we have represented this differential equation, ordinary differential equation, in the power series format. So for the solution of this, because we know that the solution of this power series is in this term, in this format. Okay, a naught plus a1 plus a2. So what we need to find is we need to find the values of a naught, a1, a2, a3. If we can find the values of a1, a naught, a3, then we will we can say that we have solved this equation. Okay, f of x represents y. Okay, f double prime of x represents y double prime. So remember that. Okay, so in order to find these coefficients am, okay, what we can do is we can do some, need to change some need to make some modifications in this. So what type of modifications are required? So what we need to see over here is that this sigma is being added into this. So I want to add these two sigma terms, but if I want to add these sigma terms, I should have the same same indexes and same powers of x. Okay, and then only I can add it. Okay, so for this purpose, what I can do is I will take the next two terms over here. Okay, so for example, there is a process which is called as, or there are two ways to look at this process. Okay, so what I can do is that I can make both terms as x power m and x power m. So this is already x power m. This term is already x power m. Is in order to make this as x power m, so what I can do is I can add the next two terms over here. So for example, if the last term is x power m minus 2, the next term will be x power m minus 1, and that again the next term, the second term after that, it will be x power m. So minus 2 plus 2. So it will be x power m. So I have increased by 2 terms over here. So similarly, its coefficient will be also increased by 2. So it will be am plus 2. And these values will be also increased by 2. So it will be m minus 1 will become m plus 1, and m will become m plus 2. Okay, and then sigma. So, but this will also affect the index terms. So the index will now, because since we have increased these two terms, so we will do the opposite with the index, and then index will become m is equal to 0, and then 2 minus 2 is 0, and then infinity minus 2 is still infinity. Okay, so so infinity will remain as infinity. So this is one way of looking at this. Okay, another way of looking at this, which is also mentioned in the book, is that, so we can assume that m minus 2 is equal to, say, s. Okay, and then s will become m will become s plus 2. Okay, so if m minus 2 is s, so this will become x power s. Okay, and then m will become s plus 2, and then m minus 1 will be then s plus 1, and m will become s plus 2, and then m is equal to 2 means if m is equal to, over here 2 is equal to s plus 2, so s will be equal to 0. So it will be s is equal to 0 to infinity. So in this case, we can also represent like this. So that is this is the more mechanical way of doing it, but that is the way I did it is like more conceptual way. So I increased by 2 terms, then the opposite I should do is to decrease the index by 2 terms from here as well. Okay, so this is the point which you should be taking care of. Then now we have left, I have these terms x power m and then a power m, and then I have the index of m is equal to 0 to infinity. So I have I don't have to make any changes into these, because m is equal to 0 is also there, infinity is also there, a power m, x power m is equal to 0. So now with this, because both of these sigma terms are at the same level, because both of these terms are at the same level, so what we can do is now we can combine these two terms. So m is equal to 0 to infinity, and then when I combine these terms, so then it will become m plus 2, m plus 1, and then am plus 2, and then am. Okay, and then x power m will be common. So that is equal to 0. Okay, because m0 infinity, and then I can add these terms. So now, in order for this equation to hold true, this term in the curly brackets should be equal to 0. Okay, so which means that m plus 1, m plus 2, or m plus 2, m plus 1, a m plus 2 should plus a m should be equal to 0. Okay, so by doing this, I get a relationship, an equation which is called as the recursive equation. Okay, recursive relationship. So minus am over m plus 1 and m plus 2. Okay, so that means what this equation tells me, that you can see that this is a relationship between these two terms, which are actually two index values apart. So am, and then the next term is am plus 1, and then after that the second term is am plus 2. So these are the two. This relationship tells us that if I want to get the a term which is two terms after that, then I can use this equation. So based on the values of these, based on the values of m, I can now get these coefficients which are needed for our solution. Okay, so I need these coefficients a0, a1, a2 in a recursive manner. So for this, what I can do is I can set up a table which is very convenient for this type of calculations. Okay, so I can set up a table, so that will be a little bit longer. I can set up a table of m values. Okay, so yeah, starting from here, starting from 0, 1, 2, 3, 4, 5, okay, maybe 6 is enough. And what I will get is am plus 2. So I will get am plus 2 values. So first am plus 2 value will be by putting m is equal to 0. What I will get is a2. The next value I will get will be a3, then a4, a2, a3, a4, a5, a6, a7, a8. Okay, and then equal to, equal to, equal to, equal to, equal to, equal to, equal to. Okay, I will get these terms. And now what I will get is each of these will be the negative. So negative, 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 negative. And what I will get in the numerator, am. So am will be a0. Okay, then the next I will get will be a1. The next I will get will be a2, a3, a4, a5, a6. So in this way we can very conveniently complete this table. So divided by, divided by, divided by, divided by, divided by, divided by, divided by. Okay, and what I will get in the numerator, m plus 1 and m plus 2. So what would be the first one? M was 0, so 1 times 2. So it will be 1 times 2, 1 times 2. And the next one will be 2 times 3. Okay, I'm using this dot for multiplication. It is not 2.3, it is 2 times 3. So 3 times 4, 4 times 5, 5 times 6, 6 times 7, okay, and then 7 times 8. So in this way, very quickly, I have got these values, but I need to just simplify these values. So for example, here I can see that A2 is in terms of A0 and A3 is in terms of A1. So what are the A0 and A1? A0 and A1 are not in terms of any other coefficients. So we take A0 and a1 as the arbitrary constants. Arbitrary constants. So just like the constant arbitrary constants in the general solution of the ordinary differential equations. So since it was a second order equation, so we need two constants a and b in this case. So these are the arbitrary constants. So in this case, in our case, a naught and a1 will be the arbitrary constants. Okay. So a naught and a1, but now we have a4, which is in terms of a2. And for a2, we know that the value is minus a naught over 1 by 2. So if I input this value over here, so this is 1 to 2, and then this is 3 to 4, and then it is minus and minus, so it is plus a naught over, I can represent it like 4 factorial. Okay, so it will be a naught over 4 factorial. Do you agree with that? It will be a naught over 4 factorial. So for a5, now it is in terms of a3. A3 is a1. Okay. So, and then this is also minus. So minus minus plus. So it will be a1 over what? Over what? 2 times 3 into 4 times 5. So which is actually, it is 5 factorial. Okay. Now the next term, a6, is in terms of a4. A4 was this plus. Okay, a4 was this plus, so minus, and then it will be minus, and then a4, and then we will replace it with a naught, and that is it. What is that? 4 factorial into 5 into 6. So 4 factorial into 5 into 6 is actually, so what I will write over here is, so we know, yeah, 4 factorial into 5 into 6 is equal to 6 factorial. So I will write 6 factorial. So similarly for this, it is a5. A5 was positive, so it negative sign, so it will be minus. So it will be a1 over 7 factorial. And then the last one, I mean, no term is the last one, but anyway, just for our calculation purpose. So the last one will be a naught plus a naught over 8 factorial. So now we can write the equation solution. So what is the general solution? So general solution is, in this case, is so what is the general solution in this case is a naught plus a1 x plus a2 x square plus a3 x cube plus a4 x4 plus a5 x5 and plus a6 x6, and then so on. Okay, so this is the solution. So now I can put it like this: y of x is equal to a naught and a1 were the arbitrary constants. So a naught plus a1 I will write like this. And what is a2? A2 is here minus a naught over 2 factorial. So it is minus a naught over 2 factorial x square. And what is a3? A3 is minus a1 over 3 factorial. So 2 times 3 we can write as 3 factorial. So minus a3 over 3 factorial x cube. And then plus this one is a naught over 4 factorial x power 4, then plus a5 over, sorry, a1 over, because a1 over 5 factorial x power 5, and then the next term is a naught over 6 factorial x power 6. The next term will be minus, will be minus a naught over 7 factorial x power 7. I think that is enough. Okay, so now I can, so this is the solution actually. Yeah, so this is the solution, but we can just further simplify this solution as this, as like this. So y of x is equal to, so now we can take the a naught terms as common, a naught into y, and then I take a naught from here, a naught y minus a naught, so it will be at 1, and then a naught I have taken common, so it will be x square over 2 factorial, and then it will be plus x power 4 over 4 factorial, and then it is minus x power 6 over 6 factorial, and then so on. And then if I take a1 as common, plus a1, it will be x, then yeah, so this was a1 actually, okay, a1. So we have answers all, we have all answers in terms of a naught and a1. Yeah, and this one was also 1. Okay, yeah. So a1 into x, and then that is a minus x cube over 3 factorial, and then plus x5 over 5 factorial, and then minus x7 over 7 factorial, and then so on. So now we can see that this is the series for cosine x, okay? This is the series for cosine x, and this is the series for sine x. So we get the same answer as over here. Okay, so in this way, then you can, by the same method, you can adopt, and then you can solve this, solve the ordinary differential equations. So do you have any questions about this method? Any confusion about the sigma notation? Yeah, you will not find this method exactly in the book for the sigma notation. So in the book it will be a little bit different, but I found that this method was more easy to follow to me, especially this tabular format and the manipulations which you can perform with the sigma notations. Okay, so if it is good understand, then you can also understandable. You can also see some more videos which I have already uploaded on the video, which I already uploaded on the Moodle. Okay, so after that there is a topic which is called as the Legendres, L-E-G-E-N-D-R, Legendres ordinary differential equation. So Legendre's equation. So Legendre's equation in itself, it is said that it is very important ordinary differential equation. And then its solution of, its solution can be represented very conveniently in this form of a power series. So what is Legendre's equation? So Legendre's equation is 1 minus x square y double prime minus 2x y prime and plus n into n plus 1 y is equal to 2. Okay, so this is the Legendre's equation. So what is the Legendre's ordinary differential equation? The y double prime term is multiplied by 1 minus x square, and y prime term is multiplied by minus 2x, and y term is multiplied by this n into n plus 1, where n is a constant, and depending on the problem which you are solving, the value of n may change. So for example, if n is equal to 1, so this equation will become 1 minus x square y double prime minus 2x y prime plus 2y is equal to 0. So I have solved this form of the equation in the uploaded video. So there is nothing different. There is the method which I have just described here. By the same method, I have solved this equation. Okay, so let's try to illustrate it a little bit more, and then it will be easy for you to also understand. So, if we want to solve this equation, so then what we have to do is we have to write what is the first step in the power series solution. Can you tell me? So we have to write y double prime, y prime, and y in their sigma notations.
Sorry, why it was 2 n multiplied by m plus 1?
Where? Oh, we can take different values of n. So for example, let n is equal to 1, then n into n plus 1 will be equal to 2. Okay, so Legendre's equation is a whole set. Legendre's equation depends on the value of n. So we can take different values of n, then we can have the different types of Legendre's equations. Okay, so this is just one case. Okay, just one particular case. Case of Legendre's equation. Okay, the general form of Legendre's equation is this. Okay, this is the general form of the Legendre's equation. So if you want to solve it, so then we have to find its write it in the sigma notation. So in this case, this equation m is equal to 2 to infinity, then it will be m into m minus 1 am x power m. Okay, like x power m minus 2. Yes, like we did it before. And then it is minus 2x sigma, then it is m is equal to 1 to infinity, and it will be m am x power m minus 1. And then suppose k is equal to n into n plus 1. Okay, yeah, because we don't want to write n into n plus 1 all the time. So just temporarily, we suppose that k is equal to n into n plus 1. So it will be then k times sigma m is equal to 0 to infinity am x power m, that is equal to 0. Okay, so in order to add up all these things, what we have to do is first of all we can multiply these terms with the sigma. So multiply 1 with this, so it will be same. I multiplied by 1, and then I will multiply it by x square. Okay, so it will be m into m minus 1 into multiplication by 1 will not change anything, x power m minus 2. Okay, and then multiplied by minus x square. So it is minus sign will remain outside. It is m is equal to 2 to infinity, and m into m minus 1 and am, and x power 2 when multiplied by x power m minus 2, it will be, because minus 2 and plus 2 will cancel out, so it will be x power m. Okay, and then minus so we can take 2x inside, so it will be 2m am, and then x power 1 and x power m minus 1, so it will be x power m. And then I can take k inside, so it will be am x power m. M is equal to 0 to infinity, m is equal to 1 to infinity, and that is equal to 0. So now if I want to combine these terms, so what I have to do is I have to bring all the powers of x equal to the same. So it will be better to bring it to x to the power m, especially for this first term. So for this first term, then it will be now m is equal to, because it will, I will need to increase by 2, so it will be decreased by 2 from here. M is equal to 2, so it is index term will decrease by the index will decrease by 2. And here m will become m plus 2, m minus 1 will become m plus 1, like just like in the previous case, and it will be m plus 2, and then it will be x power m. And now in this term, all of these terms are x is equal to m, x power m are same, but the index is different over here, right? Index starts from m is equal to 2. Okay, so if I want to change its index to 0, then what I have to do is because in this case I don't need to change this x power m term. So what I can do is I can take the first term as 0, x is equal to m is equal to 0 over here. So if, for example, if I start from m is equal to 0, then what is going to happen? Because if m is equal to 0, the first term will be, when m will be 0, the first term will be 0. If I start, then the next one will be m is equal to 1. That term will be also 0. So in this case, by changing anything, by not changing anything, I can write from m is equal to 0 to infinity, because the first two terms of this will be 0, so it will not affect anything. So it will be m into m minus 1 a m x power m. And similarly for this, I can start from m is equal to 0, because the first term will be, by m is taking m is equal to 0, that term will be 0. So it will not add anything, or it will not change anything. So I can write it like this: am x power m, and then sigma m is equal to 0 and infinity, and then k am x power m. Okay, so now because now the time is almost complete, so by now I can now all the terms can be added together, and then some of the factorization we need to put back k, the value of k is equal to n into n plus 1 as well. And after doing this, we can get the recursive relationship as follows. So the recursive relationship will be in terms of a power a m plus 2. The recursive relationship will be minus n minus m into n plus m plus 1 divided by m plus 2 over m plus 1. So into a m. So we can get this recursive relationship for the Legendre's equation. So based on the values of n and m, then we can come up with the solution of the Legendre's equation. Okay, so yeah, I will continue this topic of the Legendre's equation and the next topic leading up to the Bessel's function, and then we will be able to complete this topic maybe in the next two lectures. So, but after the next lecture on Friday, there will be a fall break. So there, I think we will be needing one more lecture after the fall break to complete this topic. But I will try to upload everything for regarding this lecture, regarding this topic on Moodle in the video format, so that you can follow along and then do the work on this topic by yourself during the fall break. Okay, so do you have any questions?